Hey guys, how are you? So in this video, I'm gonna show you how I basically can help you improve your SQL performance if you have anything that's timing out uh, beyond 60 seconds, for example. Like in this example here, I'm running a very expensive query that is going to time out in the next few seconds because it depends on how you set your superset settings, your PostgreSQL settings, where the timeout for our case is set at 1 minute, okay, 60 seconds. So what's going to happen is that this query is very slow and it's going to time out. So how do we tackle this and generate this type of results where you get things even below 1 second? Okay, so that's the goal of the video today. So let's just wait until it's timing out. Okay, it's already past the 1 minute limit. So you can see here nothing is happening. Okay, still running. So now what we're gonna do is let's copy this to another tab. Okay, right now, okay, the goal is to figure out what's going on with this with the query that we had just now that has the issue of loading and timing out, right, beyond 1 minute. So the first thing that we're going to do is we need to go back to the context of the query. What is the query all about? What is the analysis all about? What is the purpose of it? So the purpose of this analysis is to help cardiologists understand what is the who are the patients that they're serving that has abnormal readings within the last 90 days. Okay, now that's the scope of the analysis that will help us give context on how do we translate that into SQL. Okay, remember this context is going to be very important. Now, um, the next thing we want to know is we'll need to first analyze what's the row count of this table that we're trying to analyze. For example, any heart rate of the patient is recorded um, in this heart rate table, and we can see here heart rate is over 100 over million rows all time because it's a span of across like thousands of patients over the past few years. So remember, the most important thing that we need to be aware of is what is the context of the query. It is meant to be only 90 days. Okay, that's a good hint right there. Okay, so few issues with the query. So here you can see that you already have row number when you are also using this thing, okay, which is pretty redundant because you're using row number because you want to deduplicate any potential readings. Um, or if you're trying to find, in this case, we're trying to find the latest abnormal reading within the past 90 days. So we wouldn't need to do this thing, okay? So this is not required is where once we have this, okay? So what I'm going to do is I'm going to select this thing for now, okay? Then we have the correlation query that's happening on one particular column within a CTE. So this is already a CTE, and then we have a correlation query that happens within one column of this select statement, which is going to be blowing the database. It is definitely not advisable to do this, basically. So again, back to the context of the analysis. Okay, once we have the row number, right, and we remove this thing, and this is also not required. Okay, now the next thing, I saw another potential error here or performance improvement here is we don't do cross joins on large tables. Okay, because when you cross join heart rate, which is 100 million rows, right, and then you do that with a small table like all members views only contain like 500 rows, but when you do cross join, it's going to multiply that and you're going to get like 5 billion, 5 or 50 billion rows to process, and this is insane. So what I would first do is I would definitely not recommend you to do cross join, especially in CTE. Okay, because the goal here is, the first goal that I would normally do is I would figure out how do we make the data set smaller in the scope of the time frame that is the time frame scope of the analysis. Okay, remember what I told you? It was only meant to be 90 days, so we wouldn't need to go all the way back, the look back period, to all the way from the start, because that's not the goal. So I would focus on not using cross join here, okay, and left join. Here you can see this is also not needed. Casting on when doing join just add up unnecessary load to the server, so as this as well. So casting, if you show that timestamp is timestamp, the type is timestamp, the data type, the value is also in float or integer, then we wouldn't need to recast over and over again. Okay, this is only applicable if we are struggling with if the data ingested, the raw data ingested is actually not properly formatted and the format is unknown and we need to cast that, then that would be necessary to do this thing. But then we know that our ingestion engineer definitely did a great job here in making sure that the data type is correctly done, so which makes it easier for us to not do a cast again to the respective columns. Okay, so row number, this is definitely not divisible. So right now, my first goal is to reduce the number of rows of this heart rate table. We need to minimize, because it's already loading 100 million over patients' data. So we want to reduce that to probably 1 million or even 100,000. So what I will first do is I wouldn't run row number partitioning when the data of the table, the rows of the table is large. You don't do that because it does perform a rescan. You already does this first scan of the 100 million rows, and then row number just as that rescan again and again. So we don't want to do that. Okay, so what I'm gonna do is I'm gonna push this somewhere else. We will still run this second half, but it will be on a different join, on a different CTE. Okay, join as. Okay, I'm just gonna paste this. It's gonna be incomplete for the time being, but let it be like that. So we don't need org members field, which is the second table that contains all our users. Okay, so I would just add heart rates dot user ID, because we do have user ID in the heart rate. So every we use a star type schema, where all the dimensions, we make sure that it's still living in the respective matrix table, and then we have the facts table, right? So the reason why we're using star schema, because it's going to be much easier for us to do. We don't want to add load. If we were to use the snowflake type schema, it's going to add a lot of load for us to do multiple joins over and over again, so that's why we prefer the star type schema, which is more straightforward and more flat. Okay, now back to this. So what I will do is I'm gonna do from heart rates. Okay, and then we'll need to do where statement 1 equals 1. Okay, and then and we're gonna do the most important thing that we want is this. Okay, because we want the normal readings. That's the only thing that matters. We figure out what's the most important metric that we're going to use later on. Okay, so where 1 equals to 1 and or, okay, and then we leave it like that. Let's not put too much filters, because we want to make sure that filters comes later. here the first filter we want to do is we just want to perform time limiter to the timestamp so that it's only grabbing data from today and then look back 90 days. Okay, the last 90 days. That's the goal. Okay, just that. Okay, we have what we need. Okay, and then what we're gonna do is we're gonna call this filtered heart rates. Then we're gonna reference that here. Okay, so let's perform select. I'm just looking at the indentation. Okay, select from. Oh, sorry, nope, not from. From is down here already. Okay, so select row number. Okay, and then we're gonna get some of the stuff that we need. Let's see, we're gonna need all this. Okay, so we'll bring it over. Okay, we'll bring this over because we need it. But remember, because we're moving it, we're not, if we do this, we're still referencing the large tables, and we don't want that. Okay, we want the join analysis, the joining, and some filtration that we're implementing here to happen on the smaller table. So we're going to change this to filtered heart rates, filtered heart rates, and everything else should be filtered heart rates. Okay, then remember that partitioning, when you're performing partitioning, it is not required for you to perform coalesce unless you're confident that there is a null in one of the user ID column. And in our case, user ID is a serial column, is almost like, you know, and we've never allowed null for user ID. So that's why you don't really need to implement this. It's just add unnecessary load to the server. Okay, then this casting is also not required because it is already in timestamp format, and we don't want to add any further load. And the only thing we need to change here, because we did name it as reading time, so we need to change this to reading time. And then let's see what else we have here on our end. Filtered heart rate user ID is there, heart rate source. Now, because the doctors want to identify the user, okay, that's why we're performing join to another table called all members view, which contains the data of stuff like email, for example, and then awk members view full name, and awk members view username. Okay, so this is the only thing why we're performing join. But remember, we're performing join once we've make this origin table smaller. We'll call it filtered, and we're only gonna do, like, we're gonna do inner join here. Okay, inner join instead of cross join. We call it filtered heart rates, and we don't need users here. This is also an unnecessary join unless we need more information, which lives in our users table, but for the time being we don't need that. On awk members view dot user ID equals filtered heart rates dot user ID. Right, so here we would do equals to 1, and then so here we're already filtering based on 90 days. Okay, that's going to reduce the load. And then performing row number, the ranking, the order of the, we're just taking the latest rating. Oh, sorry, I need to put the SE here. So that is taking the latest rating time. Okay, based on the user ID. Now, you wouldn't need to filter by source because one of the things I want to make sure that the back to the context of the analysis is the doctor wants to see across all devices. So we're just gonna command this part here. This is also not needed. This is only needed if we know that the value, it's non-numerical or something. That's when we have this, because we want to make sure that it is only returning integers. So then we have this. Okay. So now what does this do? Okay, this is again one of my favorite thing to do is the what I call organizational clustering using Jinja, okay, which is really useful, especially in Superset. So Jinja allows us to do dynamic filtering, okay, and in our case, cardiologists will always belong to a particular organization. So when a cardiologist is making a request to a dashboard, right, it is only meant for them to load their own data. So that means so what I always like to do is when we perform Jinja filtering like this, right? So for example, do like this. So what it does is it will only scan only on for that particular organization that is requesting the dashboard. That's one request, okay? And we're making the request smaller rather than that small request because we forgot or we're not doing the organizational cluster filtering, right? Let's say we do it like that. It's going to scan throughout the whole organizations, the whole 500 plus clients, right? And that's going to be really bad on the performance. Okay, so that is why one of my personal favorite is always to implement this kind of organizational clustering, and this clustering will require you to ensure that your current tech stack supports Jinja, and making sure that you want to set this custom Jinja parameter variable on the back end in order to make this usable when we're running queries like this. Okay, so in this case I am gonna set to just one particular org, okay, for demo. Okay, so let me see if I have everything. Okay, I have, so select statement from heart rates interval 90 days and heart rate. Okay, so we want to check whether it's tachycardia or bradycardia. Okay, then row number. Okay, and then we want to make sure, yes, so this something is missing here. So from join where rn equals to 1. Okay, because now this is where we are further filtering that we don't need the whole readings. Okay, because the goal of the analysis by the cardiologist is to only see what is the latest spike and what is the latest abnormal reading across the past 90 days, right? So we only set the Rn equals to 1 so that it's taking the latest value. Then think I have everything from in the join, filter heart rates on, boom. That's pretty much that. Okay, so remember we had the issue before. It was loading at 1.1 minute and 22 seconds. So now let's see how this goes. Okay. Timestamp does it exist? Oh, okay. So line 19. So this one should be reading time because we copied it over just now. So this one is heart rate. And then this one is raw sauce. Okay, there you go. All right. Boom. Okay, under 6 seconds, right? So you can see compared to where we are having it just now, 1 minute 22 seconds until it times out. And because I stop it, it will reach timeout eventually. So, and I reduce that by just merely 6 seconds. So basically, this is how I would I would recommend you guys to these are some of the tips I would recommend you guys to follow in order to make sure that 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 dashboard doesn't time out, especially if you're building in Superset. And this is the same case even if you're using Metabase, Tableau, Looker, Power BI, those things, same principles. What I just told you is the same SQL optimizations that you can apply on those softwares as well, those tools. Because I'm just touching the what I call the fundamentals of on the SQL side. Okay, so what I'm doing is SQL level, the query level optimization. There are definitely a lot of other ways that we can do. I haven't even touched creating indexes, materialized views, or even leveraging Lakehouse like Dremio, for example, to perform what I call pre-caching. You pre-aggregate, pre-cache, pre-calculate, and kind of like cache it on their feature called reflections, which pretty much save pre-compute that data set before it is served to Superset. So again, these are some of the other ways we can look into, but I'm happy to share that in my other videos. But for now, this is pretty much what I can cover, the query level optimization. How do you actually reduce the performance from 1 minute 30 seconds to 6 seconds on 100 million rows of table? All right, so hopefully this helped. All right, cheers, take care.